We are going to start a new unit on Raman spectroscopy. We are going to cover all the titles of this unit. Raman scattering describes how light interacts with the sample to produce scattered light. The scattered light has a different energy than the incident light because the chemical bonds in the sample vibrate. When light interacts with the sample, the photons in the light can be absorbed, scattered, or pass through the sample. The scattered photons are elastic, meaning they have the same energy as the incident photons. This is known as Rayleigh scattering. The scattered photon has a lower energy and longer wavelength than the incident photon. This is known as Stokes scattering, whereas the scattered photon has a higher energy and shorter wavelength than the incident photon, and it is known as anti-stokes scattering. We are going to discuss the introduction first about Raman spectroscopy. Raman spectroscopy is an analytical technique in which scattered light is used to measure the vibration energy modes of the sample. It is named after an Indian physicist, C.V. Raman, who together with his research partner K.S. Krishnan was the first to observe Raman scattering in the year 1928. Raman spectroscopy extracts this information through the detection of Raman scattering from the sample. Raman spectroscopy is commonly used in chemistry to provide a fingerprint by which the molecules can be identified. Photons can interact with the molecules of matter in a number of ways. When they strike a solid or collection of molecules, most of them are scattered elastically, what we call this as Rayleigh scattering. But a few, 1 in 10 to the power 6, undergo inelastic scattering. When a monochromatic radiation is scattered by a substance, the scattered radiation will consist of certain discrete frequencies above and below that of incident beam frequency, in addition to that of incident frequency. These inelastically scattered photons have frequencies lower and higher than the incident frequency. This phenomenon, predicted in the year 1923 by Smeckel and observed by Sir C.V. Raman in the year 1928, is referred as Raman scattering. The lines on the low and high frequency sides of the Rayleigh line are called Stokes and anti-Stokes lines respectively. The scattered photons have frequency shifts 10 to 4000 per centimeter, characteristic of the vibrational or rotational energies of the molecule. These weak lines of modified frequencies are generally referred as Raman spectrum, and the frequency shift from the exciting line as Raman shift. When a monochromatic radiation is incident upon a sample, then this light will interact with the sample in some fashion. It may be reflected, absorbed, or scattered in some manner. It is a scattering of the radiation that occurs which gives information about molecular structure. Raman is based on scattering. Raman effect is based on scattering. The sample is irradiated with a coherent source, typically a laser. Most of the radiation is elastically scattered, called the Rayleigh scatter. A small portion is inelastically scattered, Raman scatter, composed of Stokes and anti-Stokes portions. This later portion is what we are particularly interested in it because it contains the information in which we are interested. The spectrum is measured with the laser line as a reference. Hence, the peaks are measured as a shift from the laser line. The peak positions are determined by the vibration energies associated with the bonds in the molecules of which the sample is composed. Because of this, the spectrum ends up looking very similar to an IR spectrum and is interpreted similarly. There is a footnote to this, however, as the principle of mutual exclusion applies. That is, the peaks that are emphasized in IR, what we call this as polar bonds with high dipole moments, are de-emphasized somewhat in Raman. The bands that are emphasized in a Raman spectrum are those that are due to highly polarizable bonds, such as with pi electrons. Theory of Raman scattering. When light is scattered by a molecule, the oscillating electromagnetic field of a photon induces a polarization of the molecular electron cloud. This leaves the molecule in a higher energy state with the energy of the photon transferred to the molecule. This can be considered as the formation of a very short-lived complex between the photon and molecule, which is commonly called the virtual state of the molecule. The virtual state is not stable, and the photon is re-emitted almost immediately as scattered light. In a much rarer event, approximately 1 in 10 million photons, Raman scattering occurs. It is an inelastic scattering process with a transfer of energy between the molecule and the scattered photon. If the molecule gains energy from the photon during the scattering, that is, excited to a higher vibrational level, then the scattered photon loses energy and its wavelength increases, which is called as Stokes-Raman scattering. Inversely, if the molecule loses energy by relaxing to a lower vibration level, the scattered photon gains the corresponding energy and its wavelength decreases, which is called as anti-Stokes Raman scattering. Quantum mechanically, Stokes and anti-Stokes are equally likely process. However, with an ensemble of molecules, the majority of molecules will be in the ground vibration level, which is nothing but Boltzmann distribution, and Stokes scatter is a statistically more probable process. As a result, the Stokes-Raman scatterer is always more intense than the anti-Stokes line, and for this reason, it is nearly always the Stokes-Raman scatter that is measured in Raman spectroscopy. The wavelength of the Raman scatter light depends on the wavelength of the excitation light. This makes the Raman scatter wavelength an impracticable number of comparison between the spectra measured using different lasers. Rayleigh scattering. In the vast majority of scattering events, the energy of the molecule is unchanged after its interaction with the photon. The energy and therefore the wavelength of the scattered photon is equal to that of the incident photon. This is called elastic. That is, the energy of scattering particle is conserved, or Rayleigh scattering, and is the dominant process, around 99%. So this is about Rayleigh scattering. Rayleigh scattering is an inelastically scattered radiation in which the frequency of the emission of the scattered radiation is the same as that of the excitation photon, which is nothing but H nu excitation. The scattering process without a change of frequency. So here E equals H nu x, and these are all different vibrational energy levels. So this is the ground state. These are all different vibration energy levels. So when it is excited, the electrons will go from ground state to one of the virtual energy states here, and again it will come back. So this will come back to the original state itself. Suppose if the electron starts from one level, this is one of the virtual energy states, again it will come to the same n equal to 1 level, and what we call this is Rayleigh scattering. So here Rayleigh scattering, the energy E equals H nu Ex. Next one is Stokes lines. When a beam of monochromatic light of definite frequency passes through the substance in any state, a small fraction of it is scattered due to collisions. Some amount of scattered light frequency is less than the frequency of incident light. So nu r Raman, nu r is Raman line, so Raman wave number. So nu r equal to nu I minus del nu, where del nu equals nu s minus nu I. Nu s stands for scattered wave number. Nu I is nothing but incident wave number, incident frequency. So nu r is nothing but Raman spectroscope, and nu I is nothing but incident frequency, and del nu is the shift, Raman shift, which is a change in frequency. Lines which are seen at the frequency less than the incident, they are more intense. It results in absorption process. Raman frequency carries positive sign. And when you go for the anti-Stokes line, some amount of the scattered light frequency is greater than the frequency of incident light. That is, Raman frequency nu r is nothing but incident frequency plus change in frequency. So change in frequency is nothing but nu s minus nu I. Lines which are seen at the frequency greater than the incident, they are less intense. It results in emission process. Raman frequency carries negative sign for anti-Stokes line. And here is the pictorial diagram of Rayleigh lines, Stokes line, anti-Stokes lines. And this is elastic scattering. The first one is elastic scattering, and the second one is inelastic scattering. So this is elastic scattering, and these two are inelastic scattering. So here nu s is equal to nu I, because it starts from n equal to 0 ground state to one of the virtual energy states. Again it comes back to the same state here, same ground state. So nu s equal to nu I, what we call this as Rayleigh lines. And here nu s less than that of nu I, and it starts from the ground state and it comes to one of the vibration energy states here. So what we call this as a Stokes line, and this is nothing but anti-Stokes line, and it starts from one of the vibration energy states. Again it comes to the ground state, so we call this as anti-Stokes lines. And here it is lambda plus del lambda, and here it is lambda minus del lambda. Some features of Raman lines. Raman effect is observed in gases, vapors, liquids, crystals, and amorphous solids, both organic and inorganic. Its spectral character, a more or less diffuse continuous spectrum accompanying the lines or bands. It is involving an exchange of energy between the quantum and the molecule, and the equality of the change of frequency. The possibility of an improvement in the frequency in addition to the degradation of it. It is considered as an optical analog to the Compton effect. It is also called as incoherent scattering. Some characteristics of Raman lines. The intensity of Stokes lines is always greater than the corresponding anti-Stokes lines. Raman shift, which is nothing but del nu, which is equal to nu s minus nu I, generally lies within the far and the near infrared regions of the spectrum. Raman lines are symmetrically displaced above the parent lines. When the temperature rises, their individual separation from the parent lines decrease. The frequency difference between the modified and parent line represents the frequency of the IR absorption line. The state of polarization of Raman lines varies. This is measured by the depolarization factor. Now let us discuss the classical theory of Raman effect, and thereby we are going to discuss the molecular polarizability. Classical theory of Raman effect can be explained in terms of polarizability of molecules. When a molecule is put in a static electric field, it suffers some distortion. The positively charged nuclei is attracted towards the negative pole of the field, Correspondingly, the electrons are attracted to the positive pole. This separation of charge centers in the molecule in the presence of electric field is known as polarization. Hence, an electrically neutral molecule is kept in an uniform electric field. It is polarized. The electrically neutral molecule implies that the center of positively charged particle coincides with the center of negatively charged particle. And this is pictorially represented here. And we have the neutral atom in which the center of positively charged particle exactly coincides with the center of negatively charged particle. And here, after the application of the electric field, these charges are separated. What we call this as polarization. And this is a large scale view of polarized atom. Some distortion takes place. So molecule suffers some distortion. The separation of charged centers causes an induced electric dipole moment to be set up in the molecule, and the molecule is said to be polarized. The induced dipole moment depends on the strength of the applied field E and on the ease with which the molecule can be distorted. So, mu induced is directly proportional to E, and this is called induced electric dipole moment, and this is the external electric field E, and both are directly proportional. So, mu induced equals alpha E, where alpha is known as polarizability of the molecule, and here mu is the induced electric dipole moment, and E is external electric field. It leads to an understanding of a concept basic to this form of spectroscopy, that is the polarizability of a molecule. The size of the induced dipole mu depends both on the magnitude of the applied field E, both on the magnitude and direction of the applied field E. The polarizability changes due to the applied electric field across the bond axis of any diatomic molecule. A change in polarization means a change in either magnitude or direction. On rotation, its polarization is the same in all directions. Hence, the polarizability will be circular. But along the bond axis, the polarizability is greater, so its cross-section is less. Hence, the polarizability is elliptical. For example, we can have the homonuclear diatomic molecule H2, only one mode of vibration, symmetric stretching. Here the polarizability changes and hence Raman active. They are shown in the following figure. So we have H2 molecule here, and electric field is applied in this direction, whereas we have the dipole moment is in this direction. So this is across the bond axis. See here, mu is perpendicular to E, and we have the circular shape. Whereas here, along the bond axis, so E and mu both are parallel to each other. And we have the elliptical shape. The change in size, shape, or direction of the polarizability ellipsoid of the water molecule of H2 molecule on rotation. So this is H2 molecule, not water molecule. This is H2 molecule on rotation. Let us again consider another example, a simple asymmetric top molecule H2O, whose polarizability ellipsoid is as shown in figure. In H2O molecule we have three types of stretching. First one is symmetrical stretching, another one is bending stretch, the third one is asymmetric stretching. In symmetrical stretching, the molecule as a whole increases or decreases in size. That is, when a bond is stretched, the bond becomes more polarizable as the electrons will be loosely attached with the nuclei. It results that the polarizability decreases in size when the bonds stretch and increases when they compress. So this is as shown here. So this is for the symmetric stretching mode. In the bending stretch, the shape of the ellipsoid changes the most, with the vibrations of very large amplitude on one side, the molecule approaches the linear configurations with the horizontal axis, but on the other side, it approximates to a diatomic molecule with a vertical axis. So this is as shown here. So this is for the bending mode. In the last one, in the asymmetric stretching, both the size and shape remain approximately constant, but the direction of the major axis changes significantly. In all the stretching, there is a change in polarizability ellipsoid, hence all are Raman active. They are as shown in the figure here, and this is for the asymmetric stretching mode. The change in size and shape or direction of the polarizability ellipsoid of the water molecule during each of its three vibration modes are shown here in the figure. When a molecule is subject to a beam of radiation of frequency nu, the electric field experienced by each molecule varies according to the equation E equals E naught sine 2 pi nu t, where nu is nothing but the incident frequency, and E is the electric field, and E naught is the amplitude. Thus, the induced dipole also undergoes oscillations of frequency nu. So, as substituting equation 3.3 in equation 3.2, so we have the 3.2 is here. So, we have mu induced, which is equal to alpha E times. So, alpha instead of E, substitute E naught sine 2 pi nu t. We have this equation 3.4. Such an oscillating dipole emits radiation of its own oscillating frequency. This gives the classical explanation of Raman scattering. That is, the frequency of the incident radiation and the frequency of the scattered frequency are the same. If the molecule undergoes some internal motions such as vibration or rotation, which change the polarizability periodicity, then the oscillating dipole will have superimposed upon the vibrational or rotational oscillation. The polarizability alpha is expressed as a Taylor series associated with the vibration frequency as alpha equals alpha naught plus d partial d alpha by dq times q plus 1 by 2 times d squared alpha by dq squared times q squared and goes on. And this is change in polarizability, where q is the normal coordinate associated with the vibration of a wave number. For a small amplitude vibrations near the equilibrium, that is, neglecting the higher terms, so third term and fourth term, so and so on. So neglecting the higher terms in equation 3.5 and substituting equation 3.3 in 3.5. So this is equation 3.3. So just to substitute here, we have alpha equals alpha naught plus beta q. So we have the equation, this equation. So this equation, here we have this equation. So alpha equals alpha naught. You are going to take first two terms. You are going to neglect all the higher terms. Just a substitute alpha equals alpha naught plus beta q. Instead of beta equals partial d alpha by dq. So we have 3.5 equation becomes 3.6 as alpha equals alpha naught plus beta q, where beta represents the rate of change of polarizability with the vibration. The normal vibrations are treated as harmonic as q equals q naught sine 2 pi new vibration times t, with the vibration frequency new vibrational frequency, which changes the polarizability as equation 3.6 becomes. So alpha equals alpha naught plus beta q. This becomes beta q naught sine 2 pi new vibration times t. Here alpha naught is the equilibrium polarizability, that is, the polarizability of the molecule if there is no vibration or rotation in the molecule. Now substituting equation 3.7, so 3.7 in equation 3.4, so we have 3.4 here. The induced dipole moment becomes mu induced equals alpha naught plus beta times q naught sine 2 pi nu vibration times t multiplied by E naught sine 2 pi nu t. So this equation 3.8 becomes alpha E naught sine 2 pi nu t plus this time multiplied by this time, so this term. So we have this second term. The first term represents there is no change in polarizability, whereas the second term represents there is a change in polarizability due to vibration, because we have additional frequency term. See here, new vibration. Here there is no new vibration. Here nu alone is there. So there is no change in polarizability. Here there is change in polarizability due to the additional term. So due to vibration. Using the trigonometric relation, this relation, equation 3.9. So this is 3.9. We have mu induced equals this expression. So we are going to use this trigonometric relation sin A plus sin A sin B, which is equal to 1 by 2 cos A minus B minus cos A plus B. Use this relation and this equation 3.9 becomes exactly like this 3.11. So we have now this term and this term. So we have now three terms, this first term and second term and third term, and I'm going to multiply this half beta q naught E naught, and this term becomes exactly first term, second term and third term. The first term refers as there is no change in polarizability. So the first term refers Rayleigh scattering. So there is no new vibration. Whereas in the second term and third term, we have one additional terms, and this is the argument. Just look at the argument. Cos 2 pi times nu minus nu vibration times t. Here it is plus, one is minus. And what we call the Stokes line, this is for the second term refers to Stokes line, and third term refers anti-Stokes lines. And together what we call this is Raman scattering. So these are all inelastic scattering, and this is elastic scattering. Thus the classical theory successfully describes the frequency relationships of vibrational Raman scattering. There is a change in dipole moment whenever there is a change in polarizability due to vibration. These lines are addition lines in Raman spectroscopy. This is how the Raman theory is explained from the polarizability theory of classical theory. Now let us discuss the selection rule. If the vibration does not alter the polarizability of the molecule, then beta is 0. Rate of change of polarizability. Beta is nothing but rate of change of polarizability according to this equation. So we have now three terms. The induced dipole moment. When beta becomes 0, second term and third term will become 0, and we have this first term alone, and this is for Rayleigh scattering. So there is no change in polarizability. The dipole oscillates only at the frequency of the incident radiation. In order to have a vibration or rotation to be Raman active, it must cause a change in the molecular polarizability. The general rule goes like this. In order to be Raman active, a molecular rotation or vibration must cause some changes in the component of the molecular polarizability. A change in polarizability is, of course, reflected by a change in either the magnitude or the direction of the polarizability ellipsoid. So here is the example, H2O, water molecule. The polarizability is found to be different along the three of the major axes of the molecule, which lie along the line molecular plane bisecting the HOH angle at right angles to this in the plane and perpendicular to the plane. And so all the three of the ellipsoid axes are also different. So and of course the electric field is applied in this direction, and we have the dipole moment is here, see, in the perpendicular direction. Here the dipole moment is along the direction of electric field E, and this is elliptical. The polarizability ellipsoidal axes are shown here. the water molecule and its polarizability ellipsoid seen along the three axes. Instead, the radiation can only sense the average polarizability in various directions through the molecule, and the polarizability ellipsoid, it may be shown, is always a true ellipsoid, that is a surface having all sections elliptical, possibly circular. In a particular case of H2O, the polarizability is found to be different all three of the major axes of the molecule, which lie along the line in the molecular plane bisecting the HOH angle at right angles to this in the plane and perpendicular to the plane. And so all the three of the ellipsoidal axes are also different. The ellipsoid is sketched in various orientation in the above figure. Molecular polarizability ellipsoid. The classical theory of Raman scattering is based on molecular polarizability, which is a measure of how easily a molecule's electron cloud can be distorted by an electric field. Here is some related information about Raman scattering and polarizability. Raman scattering, also known as Raman effect. This is an optical phenomenon in which a sample scatters light after the interaction with the incoming excitation light. The scattered light has a reduced energy due to the vibration modes of the chemical bonds in the sample. Polarizability ellipsoid. The axis of the polarizability ellipsoid is least where the polarizability is greatest and vice versa. Molecular polarizability ellipsoid. Induced dipole moment. When an electric field is applied to a molecule, the molecule's polarization takes place, producing an induced dipole moment. The strength of the applied electric field directly determines the magnitude of the induced dipole moment. Raman spectroscopy. The basic principle of Raman spectroscopy is that a small portion of light scattered by a molecule has a different optical frequency than the incident light. This is due to changes in the molecule's vibrational or rotational energy levels. Though the classical theory correctly describes the frequencies nu plus or minus nu vibration of the Raman lines, it fails to give correct intensities. Only the quantum theory would be able to predict the intensities.